So in the case of number 1, really conveniently, we've got the same base in both of these cases for these logs, which means that I can apply the property of logarithms that says this. I can combine these two logs into a single logarithm by multiplying the arguments together. So I can rewrite the left-hand side as log base 3 of x minus 1 times x minus 7, and then that's still equal to 3 on the right-hand side. I didn't touch that. So when the logs that have the same base are being added together, we can simplify it into a single logarithm by multiplying the arguments together. All right, our goal is to get x by itself. The way that we see it now, this log form is not helping us at all. So I'm going to switch over to exponential form and see if we can solve for x that way. So exponential form says we take our base, which is 3, we raise it to our power, which is on the other side of the equal sign here, also 3. And we set that all equal to the argument. So in this case, x minus 1 times x minus 7. All right, 3 cubed is 27, and then I've got x squared minus 8x plus 7 on the right-hand side. And I'm just going to get everything to one side and then factor. Problems like this, where I don't expect you to use a calculator, should be factorable. You shouldn't have to use the quadratic formula. So 0 is equal to x squared minus 8x minus 20. And then I can factor this into x minus 10, x plus 2. So we get two options here. X is equal to 10, x is equal to negative 2. I set those two factors equal to 0, solve for x. Okay, but remember, we're in the logs unit, which means we have domain restrictions on log. We can only take the log of a positive number. We can't take the log of 0 or any negative number. So I'm going to take 10 and negative 2, the two solutions that we got. I'm going to go up to the top, our original problem. I'm going to plug in 10 and negative 2 to make sure that I can use both of those. Now, when I plug in 10 for x into my original problem, we get the log of 9 and the log of 7. It's 3. I can do math, sorry. Log of 9 and log of 3. Both positive, both things we can do. We need a calculator to do it, but it's possible. So 10 works. We're going to box that. But when I plug in negative 2 for x, before I even get to the second term there, we end up taking log base 3 of negative 3, and that's not possible. We can't take the log of a negative number. So we have to actually cross negative 2 out. Negative 2 is not an option here. We don't box that as a final answer. So we always want to make sure we go back to the top, and we're checking to make sure that our solutions make sense and they fit the domain and range of logs. We're going to be graphing logs on Thursday, and I think we'll be able to see visually what the domain and range looks like after that. Questions on that one? Okay, number 2, kind of similar, maybe a little bit tricky because we've got a fractional base, but that's okay. So same thing, I'm going to combine everything on the left-hand side into a single log. That's the first step we want to take here. I can do that because the bases are the same. If the bases were different here, we would have a big problem. Okay, so it's always easier when the bases are the same. Now, this time we're going to take a note. The arguments here, the logs are being subtracted. So in the last example, they were being added. So when the logs are being added, we multiplied the arguments. In this case, the logs are being subtracted. So the rule of log says we're going to divide the arguments. When we apply this rule, order matters. So we always take the first argument and divide it by the second argument. So the second argument always has to go on the bottom. Just remember that. Every once in a while, I get somebody that switches it, and you'll just get the wrong answer there. Okay, so from here, couple of things we could do. The first thing I'm going to do is log form is not working for us, so I'm going to rewrite this in exponential form. So exponential form tells us 1/8 is our base. We raise it to the power of negative 2, and we set it equal to that entire argument. Okay, now here's the deal. If you can see what the left-hand side evaluates to be, then go ahead and just write it. That's fine. I would expect you guys to be able to do that. If you're having a hard time with that, here's what I'm going to do. I can rewrite 1 over 8 as 8 to the power of negative 1. And then properties of exponents tell us that if I have a power being raised to another power, we multiply. So that becomes then 8 squared, which is 64. So if you can go straight to 64, that's fine. Don't worry about showing any of those other steps. And then just to make our lives easier, you don't have to do this next step because it would work out eventually. But there's common factors on the top and the bottom that I can factor out on the right-hand side to maybe simplify. So 4x squared minus 2x, I can factor 2x out of both of those terms. And then I can also factor an x out of the bottom. So before I go any further, we can actually simplify this. I can cancel an x on the top and the bottom. The 2 doesn't go away, so I will have to redistribute, but the x's do. And that's just going to make it a little bit easier. If you didn't do this step, you guys, and you just went straight to solving for x, that's fine. They would work out. You'd get a quadratic and one of the options wouldn't end up working. But it just maybe makes our life a little bit easier. Okay, so we're here. 64 is equal to 4x minus 2 over x plus 1. And I just need to get x. We need to figure out what x is going to equal. So I'm going to multiply everything by x plus 1 in order to get rid of this fraction. And that is going to give us 64x plus 64 on the left is equal to 4x minus 2 on the right. Okay, I'm going to get everything with an x on one side, everything without an x on another. X is equal to negative 66 over 60, which is going to be negative 11 over 10. Okay, we go back to the top though. Just remember, we have to check. We do have a negative solution here. So we just want to make sure that we're good. Now, negative 11 over 10 is negative 1 point something, right? Negative 1.1. So anytime I square that number, that is going to be bigger than its original self. So when I square it in the original logs, it's always going to be, that first term will always be bigger than the second term. So we're good here. We will be taking the log of positive numbers. So we can box that as our answer. If there was no answer to box, let's say none of the answers worked out, then your answer would just be nothing. Okay. All right, stop me if you've got questions, or you can throw them in the chat. I'm going to move on to number 3. I want to give you guys as much time as possible to work on homework today. Okay, number 3, same properties as numbers 1 and 2. Our goal is to get the logs down to a single log on both sides of the equal sign. Now in this case, number 3, we've got logs on both sides, and 1 and 2 we didn't, but that's okay. We still have logs that have the same base, so it's still okay for us to combine these things. So on the left-hand side, I'm going to combine everything into a single logarithm. We're subtracting the logs, which means when I combine everything, we're going to be dividing the arguments. We're going to have 2x plus 3 over x minus 4. And then the same thing is going to happen on the right-hand side. I have logs being subtracted. They have the same base, so we can combine everything, again, using division of the arguments. So a new property of logs we haven't necessarily used, that is this. We've got logs that are the same base on both sides of the equal sign. If we get to this point where I've got one log, same base, both sides of the equal sign, we can drop the logs and we can set the arguments equal to one another. This is a property of logs. It's similar to when we're using exponents and the bases are set equal to one another, and then we can set the exponents equal to one another. That's the same kind of property. We're just applying it with logs. So if we've got logs of the same base equal to one another, then we can set the arguments equal to one another. Now it only works though if we take that first step to combining the logs on both the left and the right hand side. It only works if there's a single log on the left and the right. We couldn't go from the first step from our original problem to this, to setting all those arguments equal to one another. Okay, I'm just going to cross multiply and solve for x. Got to FOIL everything. And then we're going to see what answers we've got. Okay, once I've FOILed everything, I can start combining like terms. Conveniently, the 2x squareds go away. And then I'm going to move everything with an x to the left. I'll move everything without an x to the right. We're going to get 2x is equal to 41. So x is equal to 41 over 2. One last check to make sure 41 over 2 satisfies all of those arguments. So we have to go back to the top. If I plug in 41 over 2 into any of those cases, we will get a positive number. So we're good to go. We can box that as our final answer, and that's it. We move on. Okay, I'd say generally these problems on the test are usually ones that people get. These aren't the hardest ones. As long as you guys are good with the algebra, it's just easy to make a mistake when you're distributing a negative or something. But definitely partial credit on the test for this unit. Okay, so number 4, we're going to move on. Number 4 is going to be a different type of example. So I would maybe like star, highlight, circle 4, 5, 6, and 7. These are typically harder problems that you guys see on the test. And I'm going to do these a couple of different ways so you guys can see which option you like better. You don't have to know both ways, but I'm going to use substitution for this first example and see if you like that better than the way that I'm going to do the next problem. Okay. So we've got this 4 to the 2x minus 5 times 4 to the x minus 24 is equal to 0. And we're solving for x. X is in the exponent this time. So we are going to look at our answers a little bit differently, but we've got this and it looks a little bit complicated. So I'm going to take just a minute and I'm going to take some time to rewrite this problem. I'm going to re-represent 4 to the 2x as 4 to the power of x squared. Exactly the same thing, but it just looks a little bit different and it might make it easier to approach this problem. And then I've got minus 5 times 4 to the power of x. Now I'm going to get rid of the multiplier sign there and I'm just going to rewrite 4 to the power of x in parentheses. And then again, we're subtracting 24, not doing anything there, equal to 0. Okay, so here's what I mean by substitution. From this point on, I'm going to redefine 4 to the power of x as any variable. I'll call it u. You could pick any letter of the alphabet you want. And I'm just going to replace 4 to the power of x with this variable everywhere I see it in that first line that I wrote. So 4 to the power of x squared is now going to be u squared. And then minus 5 times 4 to the power of x is now minus 5 times u. And then that negative 24 just kind of hangs out. And we've got this. And for a lot of people, I've just found year after year, it's easier for people to see how to factor that than how to factor what's in orange right above it. Okay, totally up to you guys how you want to do this. If you can factor the orange line, you're good to go. But I'm going to factor this using the substitution. Okay, so what multiplies to negative 24 and adds to negative 5, negative 8, and positive 3? And then if I set each of these factors equal to 0 and solve for u, we get two options. U is equal to 8 and u is equal to -3. Now we're not solving for u. Our goal here was to solve for x. So I'm going to go back to where I defined what u was. U is 4 to the power of x, and I'm just going to replace u with 4 to the power of x here. Okay, we're solving for x. So 4 to the power of x is equal to 8. I'm going to get 4 and 8 in its smallest base. So 4 and 8 can be rewritten in base 2. 4 is 2 squared. So the left-hand side is 2 to the power of 2x. And 8 is 2 cubed. Rules of exponents say once the bases are the same and they're equal to one another, we can set the exponents equal to one another and solve for x. So in this case, x is equal to 3/2. Then we have this other case, 4 to the power of x is equal to -3. Okay, and just think about it. If you don't know the rule here, it's fine, but like, what number can you raise any positive number to get a negative? What could we raise +4 to and get a negative number? There is no such number. There is no number that I can raise 4 to the power of and get a negative number. So this is not going to yield any solution. If that's not something that you notice immediately, that's fine. You could take 4 to the power of x is equal to -3, and you could rewrite it in exponential form. Or sorry, logarithmic form. Go from exponential to logarithmic. And the issue is we can't have negative bases. So that's where you might be able to see more clearly that that's not going to yield a solution. Right? You don't have to write that step if you can see it immediately. Okay, now x was the exponent, you guys. We're allowed to have positive or negative exponents. So when we're solving for exponents here, x can be anything. I don't have to worry about going back and plugging it into the original problem. So 3/2 is
Why is -3 the base?
Sorry, it's not -3. It's 4. Log base 4, thank you, of -3 is equal to x. We can't take the log of a negative number. Thanks, Ron. That doesn't work. Okay. Let's do number 5. 5 looks very similar to this. Okay, in the case of number 5, I want you guys to try and factor this first, and then I'll actually finish the problem with you because there's going to be a weird way we write the final answer. But try doing the factoring of this on your own before I actually show you the work here. Thank you, Raina. Okay, there you go. One way is factored. What I just boxed would be if you don't substitute. So if you want to go straight into factoring without substitution, that's fine. It'd be 9 to the power of x minus 27 times 9 to the power of x minus 2. But we should get here, 9 to the power of x is equal to 27, 9 to the power of x is equal to 2. And then we actually need to solve for x. So in the first case, 9 and 27 can be rewritten in base 3. So on the left-hand side, we'll have 3 to the 2x. And on the right-hand side, we'll have 3 cubed. Once the bases are the same, we can set the exponents equal to each other. And we end up with actually the same answer that we had in number 4. X is equal to 3/2. But the second option is still an option. We're just gonna have to write it a little bit differently. So 9 to the power of x is equal to 2. There's no way I can get 9 into base 2. So exponential form is not gonna help us here. We're gonna have to change this over to logarithmic form. So logarithmic form says this: log base 9 of 2 is equal to x. And that's all we can do. We don't have a calculator. I don't expect you to put that as a decimal. You'll just box that as your final answer. Right, so our final answer will be expressed in one case as a log. X is an exponent, which means it can be positive or negative, so we don't have to worry about that. Okay, number 6 is for you guys to do. So I'm going to give you guys some time to do actually 6 and 7. The tricky part about 7 is actually factoring. But number 6, I'll give you guys a hint on how to start that one. 49 is the same thing as 7 squared. So 49 to the power of x is the same thing as saying 7 to the 2x. And then if I move the 32 to the left-hand side and set everything equal to 0, it becomes similar to problems 4 and 5. So take a couple of minutes, do 6, do 7, find those answers, and then we'll go through those, and then we'll finish up with 8 and 9. Okay, so let's start with number 6 first, and let's check your answers here. So the only tricky part about number 6 is making sure your final answer is fully simplified. So when I factor, I didn't use substitution in this example. So if you used substitution, your factoring would look something like this: u plus 4 and u minus 8. But you should get down to two things. 7 to the power of x is equal to -4, and 7 to the power of x is equal to 8. 7 to the power of x is equal to -4 is never going to yield a solution. I cannot take a positive number, raise it to any power, and get a negative value. So we're just left with 7 to the power of x is equal to 8. And we will never be able to get 7 and 8 to be the same base. So exponential form is no longer helpful. We're going to go to logarithmic form, and logarithmic form would tell us log base 7 of 8 is equal to x. Now, if you had boxed this as your final answer, you would not get full credit. You get partial credit there. You get most of the credit for that problem. But this is like leaving a fraction unsimplified. So the way that we make sure that our answers are fully simplified with logarithms is we make sure everything's in its smallest base, and 8 is not in its smallest base. We can rewrite 8 as 2 cubed. And when I rewrite 8 as 2 cubed, rules of log say then we can take the exponent of the argument, move it to the front as the coefficient of our log, and that's how we're going to express our final answer. So I take this power, I move it to the front, which is where I get 3 log base 7 of 2 as my final answer there. So just take that extra step to make sure that you're simplifying your final answers. I'd say after you guys practice a lot of these with homework, these are not commonly missed problems on the test, but a lot of people will forget to simplify their answers. Okay, number 7, the tricky part about 7 was the factoring, I think, more than anything. 3 to the power of x is kind of the base there. I did use substitution on this one. So I substituted 3 to the power of x for u. And I get 5u squared minus 16u plus 11 is equal to 0. And then you have to factor. So 5u minus 11 times u minus 1. Ultimately, whether you use substitution or not, you should have gotten two things. 3 to the power of x is equal to 11 over 5. And 3 to the power of x is equal to 1. So two solutions that work there. In the first case, we cannot get 11 over 5 and 3 into the same base. Exponential form isn't working, which means we have to convert that final answer to log form. Log base 3 of 11 over 5 is our first answer. And then 3 to what power is equal to 1? 3 to the power of 0 is equal to 1. So x is equal to 0 there. There's one other way I would have taken this answer. You could have also rewritten this as log base 3 of 11 minus log base 3 of 5. And that's okay unless I specified it had to be a single logarithm. So options there. All right, definitely going to see a problem like that, at least one of these on your test. Like I said, these aren't the most commonly missed problems, but they are tricky if you don't factor right or you don't simplify your answers. Okay, the last two examples for today are going to be very different than 4, 5, 6, and 7. Number 8 is going to require us to use a property of logs that I don't think we've talked about yet. So maybe you saw this last year in Algebra 2, maybe not, but we're going to have to use the change of base rule for number 8. So the change of base rule tells us this. I can take a log with any base, and I can change it, and I can pick a new base, and I can apply this to any log. The way that we're going to do this, I think it's a lot easier to see with numbers. If I have something like log base 7 of 2, and I don't like base 7, let's say I want to turn it into base 10. I take the log of my new base 10 of my old argument. So the old argument goes on the top, and I divide that by the log of my new base, and the argument in the bottom is the old base. Okay, so it's a little bit easier as we start actually applying it in examples. I think sometimes when we look at a bunch of variables and stuff like that to define the rule, it gets a little trickier. Okay, so log of new base of our original argument divided by the log of our new base of our old base. Our old base becomes the argument in the denominator. All right, we're going to apply that for number 8, and then we'll see how that helps us. So in the case of number 8, it would seem to look like number 1 or 2, but the problem is the bases aren't the same. So we can't actually combine these logs because base 5 and base 25 are two different things. It's like adding x and y, two different variables here, right? So the only thing that we can do is we can apply the change of base formula to hopefully help us work this problem out. Like I said, things should work out here. These are problems that I wouldn't expect you guys to do with a calculator, so we have to find other ways to express a final answer that should kind of work out. So what I'm going to do is I'm going to just look at the second term on the left-hand side. I'm going to focus on that, and I'm going to focus on changing that to a different base. And I'm going to pick base 5 because that's our first term. Our first term is written in base 5. So I'm not going to change the first term. I'm going to keep the first term as log base 5 of x, but I am going to change the second term to base 5. And I'm going to do that using the change of base rule. So again, the change of base rule says we can pick any base we want. And in the numerator, I'm going to have log of our new base of our original argument. And in the denominator, it's going to be the log of our new base of our old base, right? So the new argument in the denominator is the old base. Here's what I see. Change of base is one of the hardest properties to apply. It's just like naturally tricky. The most common mistake that I will see with change of base formula, and this is not one that I want you guys to make. A lot of people will use the change of base formula and do this. Okay, please don't do that. You have to have logs in the top and the bottom. It's not dividing of the arguments. You actually have to separate it out as two separate logs in the numerator and the denominator. So just don't make that mistake. Okay, and here's what I mean by things could kind of like mathematically work out, right? Log base 5 of 25. That's the denominator. What is that asking us? Well, that's asking us 5 to what power is equal to 25? That's something we should do without a calculator, right? 5 to what power is 25? Well, the denominator here is just 2. That's our new problem. Okay. And there's a couple ways we can go here. The first thing I'm going to do is I'm just going to multiply everything by 2 and clear the fraction. I just want to get rid of that fraction. So I have 2 log base 5 of x plus log base 5 of x squared minus 24 is now equal to 2 on the right-hand side. And our goal here is to solve for x. We're getting close. We applied the change of base formula to hopefully allow us to combine everything on the left-hand side into a single log, but there's one step we have to take before we can do that. We are really close on the left-hand side to getting everything down to a single base. However, we can only combine the logs when the bases are the same and the coefficients of the logs are 1. We have a problem because we've got a coefficient here that is not 1. We've got a 2 in front of this log. So I've got to get rid of that. I've got to take care of that before I can combine these logs. Now, the way that I'm going to do that is I'm going to go backwards with that power rule. I can rewrite this as log base 5 of x squared. And once I've got this, now we can combine the logs on the left-hand side by multiplying the arguments together. So I can make this a single log of base 5. And my argument is now x squared times x squared minus 24. All right, our goal here is to get x by itself. So logarithmic form no longer helping us. I'm going to rewrite this in exponential form. This is 5 squared is equal to x to the 4th minus 24x squared. I'm just going to distribute the x squared to both of the terms there. And then I'm going to get everything on one side and see if I can factor this. All right, I can factor that in an x squared minus 25 times x squared plus 1. And when I set each of those factors equal to 0, we get two things. X squared is equal to 25. So if I solve for x there, x has to be 5 or negative 5. Remember, if we take the square root of a number, we get two options. And then over here, x squared is equal to negative 1. To get x by itself, we take the square root of both sides. We are not dealing with imaginary numbers, so we don't worry about that one. We will talk about imaginary numbers next semester, but for now, everything should be real answers. Okay, so before we box our final answer, we do have to go to the top and we have to check to make sure that they both fit in the original problem. So let's talk about that first term, log base 5 of x. If I plug in positive 5, we're good to go. However, if I plug in negative 5, I can't take the log of a negative number. So negative 5 doesn't get included in our final set of solutions. X is equal to 5 is the only option there. Okay, so change of base rule. There'll probably only be like one problem on your test related to the change of base rule, but just make sure you know how to apply it. Really practice the homework problems that require that.
For the 2 log base 5x, why do you have to make it into an exponent again? Sorry.
Oh, okay. So we can only combine logs when the bases are the same and the coefficients are 1. So we have to move the 2 up to the top here in order to get the coefficient of that first term to be 1 before I can combine the logs.
Also, why did we cross out log to the base of 5, or like 25 to 2?
Okay, so log base 5 of 25, what is that equal to? Well, that in exponential form would look like this, right? 5 to what power is equal to 25? That is 2. So that's where the 2 comes from. It just equals 2. All right, other questions, guys? Good questions. Tough problems. You got to show all of your work there. So answers only on the test are going to get you 0 points. So you want to make sure you're showing all of the algebra there and all of the properties. All right, one last example today. Here's the deal. I would say this is probably the most commonly missed question on the test every year. A question that looks like this. The more you practice something like this, the easier it's going to be for you guys when you get to the test. There is, for this type of problem, one way to approach it, which is kind of nice. So if you know that one way and you can practice that one way over and over again on the homework problems, it should make the test a little bit easier. Okay, but here's what we're doing. We're solving for x here, and we've got something that looks kind of ugly. So the first thing I'm going to do before I do anything else is I just want to get rid of this fraction. I don't like the look of it. I want to just get rid of the 2. So I'm going to multiply both sides by 2. And that's going to leave me with e to the x plus 2 on the left is equal to 48 times e to the negative x. All right, once I've taken care of the fraction, we have something that looks maybe less complicated, but we're solving for x and we have positive x power and a negative x power. And here's where a lot of you guys are going to go. And I don't want you to do this. Okay, so don't do this. Don't write this step down. But a lot of people are going to do this. They're going to take that negative x on the left or the right hand side and they're going to pull it down in the denominator. And it's going to make your life a little bit more complicated. Well, it might not. But here's the best step you can do. Okay, instead of doing that, the general rule is I'm just going to multiply everything by e to the positive x. And we'll see what happens. And then if you do this step for every problem that looks like this, you guys will be good to go for your test. Okay, this next step, you guys don't have to worry about showing, but I will show it in lecture so you guys can see what's happening. I do have to distribute that e to the power of x to every single term. What happens is this. We get e to the power of x times e to the power of x plus 2 times e to the power of x. This is equal to 48 e to the negative x times e to the positive x. Okay, if you can simplify this in your head, you don't have to worry about writing that step. But I just wanted to show you guys what happens. When I have bases that are the same being multiplied together, the rule is that we add the exponents. So e to the power of x times e to the power of x, that's e to the power of 2x. And then the 2e to the x, that just stays. There's nothing I can do there. But again, we've got some math magic happening on the right-hand side. E to the negative x times e to the positive x. Rule is we add the exponent. So that's e to the negative x plus x, which is e to the 0, which is just 1. It conveniently goes away and leaves us with just 48. And then if I move that 48 to the other side, subtract it from both sides, we get a problem that looks like number 4 or 5 from our set of examples. It becomes a factoring problem. So either you could substitute, you could say u is equal to e to the power of x. For the sake of time today, I'm just going to factor this for you guys. All right, I need two numbers that multiply to negative 48, add to positive 2. That's going to be 8 and 6. And so we get two options. E to the x is equal to negative 8, or e to the x is equal to 6. Now, e to the x is equal to negative 8, not possible. E is a number. It's like 2.71 something. It's like pi, right? It represents a number. We just use a variable instead. So I still can't take 2.71 and raise it to any power to get a negative, but we can work with e to the x is equal to 6. So exponential form not helping us there. We're going to change it over to log form. This says log base e of 6 is equal to x. You will never box your answer like that. You will never write log base e. Okay. Instead, log base e is always that natural log. 6 is in its smallest base, so that is simplified after that. Final answer there, you're good to go. So if you do homework problems, if you see a homework problem like that, approach it that way. There's other ways you could do it, but I think this is the easiest and straightforward way to do it. And you should be good to go on your test question that looks like that then.